My name is Gabriel Fonseca, and I am a PhD student at PUC Minas and at ESIA Paris in a joint supervision. And today I'm going to present to you the work that I've been developing during my PhD. It's work that it's in the context of my PhD subject. The subject of my PhD is learning markers for marker-based image segmentation. And this work that I'm going to present to you is in this context. And it's about fuzzy marker-based segmentation using hierarchies and how to use it with neural networks to automatically propose markers. So brief introduction, image segmentation consists in partitioning an image into different regions of interest. And but sometimes creating good automatic segmentations can be challenging. And one way to cope with this problem is to add information, user information in the form of markers. So markers that have information about the location of objects of interest. In this work, we use as a base for a marker-based segmentation method, the one proposed by Salambier and Garrido, in which we have a pair of markers, so an object and a background marker. And these markers, they are propagated over a hierarchy constructed over the image to produce a segmentation. In this, generally, in classical marker-based segmentation methods, markers, they have a binary nature. So either a pixel of the image is marked or not. And what we are interested here is in the scenario where markers are fuzzy instead of being crisp. So here we have an example of two different type of markers. On the left, we have crisp markers that have the binary nature. So here, either a pixel of the image is marked or not. And on the fuzzy markers, we can see that depending on the location of the marker, we can have different intensities for the marker. So the outline of this presentation is the following. I'm going to present a marker-based segmentation using hierarchies. So then I can present our extension to the case where markers are fuzzy instead of being crisp. And finally, show how we can use the fuzzy marker-based segmentation with neural networks to learn markers and show some preliminary results of this study. So beginning with the marker-based segmentation, I need some to define, so give some basic definitions first. We define the image domain as a set V, and we define markers as subsets of V. So here we have an example, an illustration of a set V with 4 elements and 2 markers O and B that stand for object and background that are composed by subsets of V. We also define hierarchies on V. So a hierarchy H on V is a set of subsets of V such that V is an element of the hierarchy. And for every element X in V, the singleton also belongs to the hierarchy. And for every 2 elements in the hierarchy, they are either disjoint or nested. And we also define indexed hierarchies, which is a pair, H omega, where omega is an index function, is a function from H to the real positive numbers, where the index of an element is equal to 0 if and only if this element is a singleton in the hierarchy, and for every 2 elements X and Y in the hierarchy, if X is included in Y, then we have that the index of X is smaller than the index of Y. Now I'll present the notion of connection values based on ultrametric distances. And I use these notions to present a different characterization of the segmentation method, the marker-based segmentation method. And this characterization allows us to present afterwards our extension to the case where markers are fuzzy. So an ultrametric distance between 2 elements is the index of the smallest region of the hierarchy that contains both elements. And we define as connection value between an element X and a subset Y as the shortest ultrametric distance between X and every element of Y. So with these notions, we can define the marker-based segmentation with respect to a pair of markers, O and B. So the object segmentation is given by every element X in V such that the connection value of this element to the object marker is smaller than the connection value of this element to the background marker. So here we have an example of such segmentation. We have an image followed by a marked image with two marks, the blue one for representing the object marker and the red one representing the background marker, followed by a saliency map representation of a hierarchy constructed for this image. And at the bottom, we have the map of connection values to the object marker, followed by the map of connection values to the background marker, and they produced segmentation. In this map of connection values, the darker colors mean lower values. And we can observe that for the produced segmentation, every pixel that is included in the produced segmentation have a connection value to the object smaller than the connection value to the background marker. So now that I presented the marker-based segmentation, I'll present our extension to the case where markers are fuzzy. But first, we need to define fuzzy markers. So here we represent fuzzy markers by fuzzy sets. So fuzzy set mu is a function from V to the real interval between 0 and 1. And for every element x in V, the value mu x is the membership degree of the element x in the fuzzy set mu. So for instance, if you have membership degree of 1, it means that the element is fully included in the fuzzy set. If we have a membership degree of 0, it means that it's not included. And if we have a membership degree between 0 and 1, it means a partial inclusion of the element in the fuzzy set. With the notion of fuzzy sets representing fuzzy markers, we can extend the connection values that I presented before to fuzzy connection values. And the fuzzy connection value of an element to a fuzzy set is defined by the following equation. And we can analyze this equation, dividing it into two terms to make things a little bit easier. The second term, it plays, the idea behind the second term is that it plays the same role as the connection value that I presented before. These terms 1 minus mu I, they are here more for technical reasons. They allow us to show some properties of our method. But the main idea of this second term is that it plays the same role as the connection value before, as we can see by the autometric distance between two elements. And we introduce the information of the membership degree of an element to the fuzzy set by this first term, which is this alpha function of mu I. And the alpha function is a positive decreasing function such that alpha 1 is equal to 1. So the idea behind it is that the intuition behind it is that if we have element with a membership degree of 1, so if mu I is equal to 1, alpha mu I will be equal to 1. But as we decrease the membership degree of y in mu, so as mu I decreases, the value of alpha mu I will increase. So we want basically that elements with low membership degrees lead to high fuzzy connection values. So with the fuzzy connection values, we can define the fuzzy marker-based segmentation similarly to what we did before. So the fuzzy marker-based connection, the fuzzy marker-based segmentation for a pair of two fuzzy markers, mu O and mu B, is given by every element x in V, such that the fuzzy connection value between x and mu O is smaller than the fuzzy connection value between x and mu B. And here we have a similar example to what we had before. So we have an image followed by an image with markers, but now I don't know if you can see it well, but the markers are fuzzy. And followed by a saliency map representation of a hierarchy for this image. Below we have the maps of fuzzy connection values to the to mu O and mu B, the fuzzy connection, the fuzzy marker, fuzzy object marker, and fuzzy background marker. And finally, the produced segmentation. And similarly to what we had before, every pixel in the produced segmentation has a fuzzy connection value to mu O smaller than the fuzzy connection value to mu B. We also show that if we have two markers, O and B, that are subsets of V, and we have two fuzzy sets that are indicator functions of O and B, then the fuzzy marker-based segmentation with respect to the indicator functions is the same as the marker-based segmentation with respect to the subsets O and B. So in other words, it means that if we have fuzzy sets that represent crisp markers, we show that our extension produces the same result as the original method. We also propose a linear time algorithm for computing the fuzzy connection values. So we show that we can, with one pass over the hierarchy from leaves to root, followed by one pass over the hierarchy from root to leaves, followed by one pass over the elements of V, we can compute the fuzzy connection values for every element in V to a fuzzy set in linear time. And consequently, we can compute the fuzzy marker-based segmentation also in linear time. So now that I've presented the fuzzy marker-based segmentation, I'll show you how we use it with neural networks to produce a marker learning system. So the problem that we want to tackle here is that given an image segmentation dataset, we want to learn a dictionary of markers, so a pair of markers for each image in the dataset, such that these markers are able to recover the segmentation ground truth if they are used in a marker-based segmentation, and also follow some shape constraints. And when I say follow shape constraints, what we want is that the markers, the produced markers, they look like something that could be given by humans. So we don't want, for instance, that the markers are too big in the same size of the object, because if they have the same size of the object, it would be basically a segmentation, not characterize well a marker. So we want them to recover the segmentation and also follow some shape constraints. And the overall architecture for doing that is the following. We have an image plus the segmentation ground truth as input to a marker creation network, which in our case is a UNet with a pre-trained ResNet 18 as encoder. And we have as an output of this marker creation network a pair of fuzzy markers, so one for the object and one for the background. And we do two main things with these fuzzy markers. We first produce a fuzzy marker-based segmentation with the produced fuzzy markers, and compute a segmentation loss between the output segmentation and the segmentation ground truth. And we also compute a set of regularization functions over the fuzzy markers. And these regularization functions are the functions that allows us to enforce some of the constraints, some of the shape constraints that I mentioned before. And in the end, the total loss that we want to minimize is a weighted sum of the segmentation loss plus the set of regularization functions. For the preliminary results that I'm going to show you, we use the Wiseman 1 object dataset. For the hierarchies, we used a watershed by area hierarchy created over graphs of set gradients. And in the experiments that I'm going to show, we are learning only the object marker and using the frame of the image as a background marker. So here we have some results. From left to right, we have the input image followed by the segmentation ground truth, followed by the learned object marker, and a fuzzy segmentation, which is produced using the object marker and the frame of the image as the background marker. So what we can see, what we observed with these preliminary results is that we are indeed able to produce some markers that follow some shape constraints. So they look, I would say that they look like scribbles that could be produced by human beings. They are smaller than the object at least. They are somehow smooth. So the shapes, we are happy with the shapes that we produced. But some of the segmentations, as we can observe, they are not ideal. So for instance, in this third example, we have parts of the object that are leaking into the background. And in the second object, we have parts inside of the object that have lower values than the background. So this is not desirable also. So the conclusions of this work is that we propose an extension of a classical marker-based segmentation method to the case where markers are fuzzy. We show that when fuzzy markers represent crisp sets, the proposed method produces the same result as the original one. We also propose a linear time algorithm for computing the fuzzy marker-based segmentation. And we show some preliminary results on how to use the fuzzy marker-based segmentation with neural networks to propose automatically propose markers. As future works, we want to continue studying the automatically proposal of markers and work better on the balance between good segmentations and good-looking markers that we have not achieved it as it is for now. We also want to create a generic marker proposal network, so removing the segmentation ground truth as the input, as we are using right now. And in the future, also including user interaction in the marker learning pipeline, so we can, for instance, learn from user corrections, so we can propose better markers in the future. So that's it. Well, thank you very much for your attention. And if you have any questions, I'll be happy to answer them.
Thank you, Gabriel, for this very interesting presentation.